The last assignment was kind of programming oriented. This assignment is somewhat more theory oriented and requires doing derivations and such. In the last assignment, we saw the importance of the concept of the Tonti diagram. We saw the significance of the B matrix and how the B transpose matrix relates to equilibrium, how we can deduce things like the principle of virtual work from the Tonti diagram and so on. But we kept our discussion kind of focused on a discrete structure, namely the truss. In this assignment, we are going to focus on continuum systems. We'll see what the difference between a continuum system and a discrete system is in the very first video. We're going to develop notions of strain and things like that for a continuum, and eventually build Tonti diagrams for continuum systems. We'll again be able to deduce things like the principle of virtual work from the Tonti diagram. So the videos, as before, will bring in concepts of mechanics, calculus, and linear algebra, put them together. And there will be two continuum systems that the videos and the exercises will cover, namely a one-dimensional axially loaded bar and a two-dimensional continuum. What this assignment asks you to do is, in part 3, to extend that idea from a 2D continuum to a 3D continuum. And then in part 2, we're asked to explore a Timoshenko beam. In a lot of the undergraduate mechanics courses, we make the assumption that the beam is long and slender, and therefore shear deformations are negligible, and we call that approximation an Euler-Bernoulli beam. Timoshenko beam is an approximation where shear deformations aren't small and have to be included in the calculation. So problem 2 is about constructing a Tonti diagram for a Timoshenko beam. And in the videos and exercises, we develop things related to strain in the 2D case. Exercise 1 in this assignment is a MATLAB grader problem that involves extending those ideas from 2D to 3D.